Hello, everyone. Thank you. I'm really honored to present you some data straight off our lab at the IFA. So we analyzed the impact of back supporting exoskeletons on gait. So as you may have heard, supporting effects have been reported or analyzed for exoskeletons, back supporting exoskeletons, for static holding conditions and for dynamic lifting. And in best cases, if the weight or if the weight is high and you place everything on the ground, the exoskeleton will work really well. So that's so if you want to maximize your supporting effects, the working conditions have to be really, really bad, and then you can reach like a peak lumbar moment reduction about 20%. That's the best case for an exoskeleton to work. But if you already change like the height of the loading, the height of the box, for example, from knee height to close to hip height, the exoskeleton will not work that much like before in the worst condition. But that's not the topic of my talk, because since many physical demanding jobs require at least short walking distances, an exoskeleton should not interfere with level walking. So we have all the conditions where you just go to grab something or you go just for a short walk. And in these situations, the exoskeleton should not interfere your gait patterns. So our research question was, do joint kinematics and joint loading differ between an exoskeleton condition and a non-exoskeleton condition during level walking? We had the set of independent variables, which were the conditions. So we had one condition without an exoskeleton, we had a condition with an active exoskeleton, one condition with a passive exoskeleton, and a second one with another passive exoskeleton. And we analyzed as dependent variables the knee flexion angle, the knee flexion moment, the hip flexion angle, and the hip flexion moment. We had 12 subjects, 6 were female, 6 were male, and they had all every subject had to was exposed to every condition of the 4 conditions, and we had the level walking trial repeated 3 times. We then analyzed the movement using our mocap data, our motion capturing system. It was our Vicon system, a 12-camera system with infrared cameras and markers, optical markers placed on the anatomical landmarks of the subjects. We recorded ground reaction forces with 2 pause plates in the middle of the walkway, and used this data to run an inverse dynamics analysis to calculate from the external forces the forces in the knee and in the hip joint, or the moments to be exact. So we had the parameters, the 3D joint kinematics for the knee joint, for the hip joint, and the loading, the corresponding loading, the knee flexion moment and the hip flexion moment. 4 conditions, 3 are displayed. So I don't want to give you any names about the exoskeletons because I don't want to prefer any exoskeleton over the other. But what this graph should show you, they work all different. So the design of the exoskeleton is quite different, and we had 1 active and 2 passive exoskeletons. This is our movement try. So our subjects were working above the force plate, turning. This was the first repetition, second repetition, and the third. As we were not analyzing any asymmetries between left and right, we treated the left face and the right face, or the left leg and the right leg, as the same. So from the whole gait cycle, we analyzed the stance phase, which starts with the foot strike, the green bar, and ends with the toe off. This was the phase we were analyzing, the stance phase where our foot is placed over the force plate. So we defined the foot strike as 0% stance phase and the toe off as 100% stance phase. Then you get a graph. This is the one example for the knee flexion angle. You have the stance phase starting with the toe off and with the heel strike and the toe off in the end, or foot strike and toe off. Then it's normalized from 0 to 100%, and usually you make something like a discrete statistical analysis, so you have the minimum and the maximum value or the range of motion, and you analyze this. But what we did was we used continuous data analysis, SPM, to analyze the whole data series. So it's not just one single point, we analyzed the whole data series between the conditions. For this, you have the dependent variables, you have to time normalize them to the stance phase, and then we check them for normality, and if there was a violence to normal distribution, we took the non-parametric version of the test, and if not, we took the parametric version, and in the end we made a post-hoc analysis. In the post-hoc analysis, we compared the no exo condition with the active exoskeleton condition with the passive exoskeleton condition 1 and the passive exoskeleton condition 2. And that's the first example of the data. So we have the no exoskeleton condition versus our first, or the active exoskeleton. And as you see here, this is our T-curve. And in SPM, if the T-curve exceeds the threshold values, there's a lower one and a higher one, then you have a statistical significant difference in both curves. In this case, happy days, no difference in both curves. I have a second example for you. This was the second passive exoskeleton. And here you can see we have in the early phase of the stance phase, we have 14.2% difference, and then in the middle of the stance phase, 39.9%. We took this information and calculated accumulated difference to give you one value where you can compare all the exoskeletons. So in this case, the second passive exoskeleton had 54.1% statistical difference in the stance phase in the knee flexion angle. These are the results for every combination. So the knee flexion angle I showed you, the first example was 0%, so there was no statistical difference, and the worst case for the knee flexion angle was the second exoskeleton with 54.1%. In the middle, there was also no significant difference. What was great to see was also that the knee flexion moment was really low, so there was just in one condition 1% of the stance phase differing for the knee flexion moment. The hip flexion angle and the hip flexion moment, they are grayed out for this time because we had the problem, or we were facing the problem that if you have the exoskeleton on your hip and you track the hip with optical markers, the markers are hidden. So you have to reconstruct the markers from the hip from external markers on the exoskeleton. And my colleague Jasper Jones is actually working on, he's working on a reconstruction method to reconstruct from the external markers on the exoskeleton the markers for the hip joint to better track the hip joint movement. So this is for now grayed out. We calculated with this with the current phase. We calculated the data with the current model, but we have to improve our methods in this case. So to round it up, so the impact on knee joint kinematics could be more attributed to the design. So of the exoskeleton, so not every exoskeleton is influencing the hip joint movement in the same way. The impact on knee joint loading was really low, so just one exoskeleton showed 1% difference there. And the exoskeletons are mostly tightened, or the back supporting exoskeletons are mostly tightened to the hip. So to really to analyze the hip, which is in the exoskeleton, we further have to improve our methods to track the hip inside of the exoskeleton. Yeah, and to complete it all up, if we fixed the hip joint movement, we will add the ankle joint movement, because you can't just analyze a complex human movement by just one or two joints. You have always to encounter the complete kinematic chain. So there will be an analysis of the ankle joint, the knee joint, and the hip joint. Thank you.
you.